Hello viewers, I am BSSP Rajashekhar, Assistant Professor of Mathematics, Government Degree College for Women, Nalgonda. In today's video, let us discuss about linearly independent sets. But before going into linearly independent sets, we need to have an idea about echelon form of a matrix, reduced echelon form of a matrix. Let us do some exercise on converting a matrix into reduced echelon form, and later we quickly recap the definition of vector space and subspace which is useful in this concept. Let us go through linear combination and span of vectors definitions. Later we move on to linearly independent sets, and we will look into some of the examples on linearly independent and dependent sets in this class. Let us first move on to echelon form of a matrix, which is very useful in solving the problems, in identifying the vectors, whether they are linearly dependent and independent and find basis, etc., which we are going to come across in the future classes. So let us first discuss about echelon form. So what is an echelon form of a matrix? A rectangular matrix is in echelon form or row echelon form if it has the following three properties. So a matrix is said to be in echelon form if it satisfies the following three conditions. The first one is all non-zero rows are above any rows of all zeros. So all non-zero rows must be below the non-zero rows. All the zero rows must be below the non-zero rows. That is the first condition. Non-zero rows are above the rows of all zeros. This is the first condition. Next, second one. Each leading entry of a row is in a column to the right of the leading entry of the row above it. So leading entry of a row in a column is to be the right of the leading entry of the row above it. Let us look into it through an example. Now the third condition is all entries in a column below a leading entry are zeros. All the entries in a column below a leading entry are zeros. So if these three conditions are satisfied by a rectangular matrix, then we can say that it is in echelon form. Let us look into this through an example. The following matrices are in echelon form. The leading entries may have any non-zero value, that is denoted by this black square box, and the starred entries may have any value including zero. So this is a model for this is an example for echelon form. So here let us see whether all the three conditions are satisfied or not. All the zero rows must be below the non-zero rows. Here these two are zero rows. These are below the non-zero rows. This is the leading entry. Leading entry must be right to the each leading entry of a row is in a column to the right of the leading entry of the row above it. So this is the leading entry. This is the first leading entry, and second leading entry is right to this one, and third leading entry must be right to this one, and there is no other leading entry in this matrix. So that is the second condition. Now the third condition is all entries in a column below a leading entry are zeros. So here you can observe that all the entries below this leading entry are zeros. Similarly, all the entries below this leading entry are zeros. Let us look into another example. Here, first, first column have all zeros, so there is no leading entry. This is the leading entry. Leading entry is nothing but first non-zero element of a row. So it is the leading entry. And all the entries below this leading entry are zeros. And in the second column, this is the first non-zero element. That's why it is the leading entry. It is right to the first leading entry. And all the entries below this leading entry are zeros. And next in the third row, this is the first non-zero element, that is leading entry. It is right to the previous leading entry. And all the entries below this are zeros. And this is another leading entry, which is again right to this one. And all the entries below this leading entry are zeros. And finally, in this fifth row, this is the first non-zero element. That's why it is the leading entry. It is right to the previous leading entry. So all the three conditions are satisfied by these matrices. So these two are the models for a matrix to be in Echelon form. So here, these boxes, these block check boxes, square boxes, can be filled with any non-zero value. Here you may put 5, -7, anything except 0. If it is 0, this will not be leading entry, then this will be leading entry. So this should not be 0. That is the only condition. Any real number you can take as the leading entry. And in the place of stars, you can put any value including 0. Zeros can also be placed here. So 5, 0, 0, 0, 3, 0, 0. That is also in Echelon form. So this should not be 0. That is the condition. The leading entry must not be 0. The first non-zero entry in a row is called leading entry. That should not be 0. Since we are saying that non-zero element. So this is the form of Echelon form. So let us look into some more examples of Echelon form. This matrix is in Echelon form. So this is the leading entry, and this is the leading entry, and all the zero rows are below the non-zero rows, and all the entries below the leading entry are zeros. So this is an example for Echelon form, and this is another one. We can observe that this is the leading entry, and all the entries below this 3 leading entry are zeros, and 2, this is another leading entry, and this is 0. The entry below the leading entry is 0, and this one is the third leading entry. So 3, 2, 1 are the leading entries. So this is another example for Echelon form. So here 1, 2, this 2, and this 1 are the leading entries. Later we call it as pivot positions. So all the entries below the leading entry are zeros. Here these two are zeros, here this one is 0, and there is no entry below it. So these matrices are in Echelon form. So this is the Echelon form. Let us move on to reduce the Echelon form. If two more conditions are imposed on this one, that will become reduced Echelon form. If a matrix in echelon form satisfies the following additional conditions, then it is in reduced echelon form, or we can call it as reduced row echelon form. So those two additional conditions are: one, the leading entry in each non-zero row is 1. In echelon form, it need not be 1. You can take any scalar. But in reduced echelon form, that leading entry must be 1. That is the condition number 4, additional condition, first additional condition. And the next one is, each leading one is the only non-zero entry in its column. So that should be the only non-zero entry in its column. These two are the additional conditions on echelon form to become reduced echelon form. So in this one, so here we have 3. This should be 1. And here it is 1. But there should not be other entries in this column. These two must be zeros. And this should be 1. This should be 0. So that it is in reduced echelon form. So this matrix is in echelon form. If we want to convert this into reduced echelon form, we have to make it 1, and this is 0, and these two are zeros. That is the reduced echelon form. So let us see the examples of reduced echelon form. So the following matrices are in reduced echelon form. Because the leading entries are 1, leading entries must be 1, and there are zeros below and above each entry, each leading 1. So in echelon form, there must be zeros below the leading entry. In reduced echelon form, there must be zeros above and below the leading entry, which should also be 1 only. So it is a form of reduced echelon form. So it will be in this form. This is the model for that. So here in place of star, you can add anything, any scalar, including zeros. So leading entry here, it must be 1, no other scalar, and all are zeros. And this is the second leading entry. It should also be 1, and there will be no other non-zero entry in that column. In reduced echelon form, this must also become 0. This is also 0. In echelon form, it may not be a 0. Similarly, it is a much bigger matrix. So first column is of all zeros. So this is our leading entry, and all zeros. And this is another leading entry. All the entries in this column are zeros. You can observe that this is another leading entry. All are zeros except this one. Similarly here. So in each column where there is a leading entry, that is the only entry, that is also 1, and remaining are zeros. Where there is no leading entry, you can put anything here. In this place, any scalar can be used. So all the star marks can be filled with any number, including 0. So this is the form of reduced echelon form. So reduced echelon form will be in this form. Let us look into some more numerical examples of canvas. So this is a matrix which is in reduced echelon form. So here you can observe that these 3 are leading entries, 1, 1, and 1. These 3 are leading entries. And in this one, so first, second, and fifth columns have leading entries, and all other entries are zeros in these columns. So it is in reduced echelon form. Here you can have any number, any scalar. So there is no conditions on this row, in this column also. Since there is no leading entry here. So actually these columns are called as pivot columns. We'll look into it a little later. So this is another example for reduced echelon form. Here too you can observe 1, 1, 1. These are the 1, 3, 5 columns are pivot columns which have only zeros and leading entry as 1. And this is one more example on reduced echelon form. This is a leading entry and all zeros. This is a leading entry, all zeros except that one. And this is the leading entry. There is no leading entry in this column and in this column. Second and fourth columns does not have leading entries. So there is no condition on this 4 and 2. So these are the examples of reduced echelon form. Let us discuss about pivot position. The leading positions are called pivot positions. A pivot position in a matrix A is a location in A that corresponds to a leading one in the reduced echelon form. If you convert the matrix into reduced echelon form, then the positions occupied by one will be the pivot positions. For example, in this matrix, this is a pivot position. And this is a pivot position. Here you can observe that this is not 1. Actually, this is not in reduced echelon form. This matrix is in echelon form only. But this can easily be converted into reduced echelon form. By dividing the second row with -2, you will get 1 simply. By dividing fifth row with -5, you can get 1 here. Using this one, you can make these two zeros. Using this one, you can make this one 0. So it is easy. Once you have got the echelon form, it is very easy to convert into reduced echelon. But the positions of leading entries, where one will come, leading entry should be 1 in reduced echelon form. Those positions will be the pivot position. So these are the pivot position. This is the pivot position, and this is another one, and this is another one. These three are called. These three positions are called pivot positions. The matrix. Similarly, and this is another example. Here, this position is called pivot position. So the only condition is this should be a non-zero. If it is non-zero, we can convert it into 1 later. So these square boxes should be filled with any non-zero scalar. These star marks can be filled with any number including 0. So these three are the pivot positions. Pivot column. The pivot column is a column of matrix that contains a pivot position. So, in the previous example, this is the pivot position. So this is the pivot column. This is another pivot position. So this is another pivot column. And the fourth column, it contains a pivot position -5. This one, this position is called pivot position, and the column which contains a pivot position is pivot column. So here 1, 2, 4 are the pivot columns. Here we have 5 columns, 1, 2, 3, 4, 5. Out of them 1, 2 and 5 are the pivot columns. Column number 3 and column number 5 does not have pivot positions, so they are not pivot columns. So let us convert a matrix into first echelon form and later into reduced echelon. So this is the given matrix, 3 by 6 matrix. It has 3 rows and 6 columns. It's a 3 by 6 matrix. Let us convert it into echelon form. So as a step 1, we begin with the leftmost non-zero column. This is the pivot column. So this is the leftmost column. If it contains all zeros, then we move on to this column. Now this is a non-zero column, so it is my first pivot column. So first we need to identify the first pivot column. If there are all zeros in this column, this will be our pivot column. If these two contain all zeros, then this will become pivot column. In this example, it is a non-zero column. That's why it is our pivot column. So in this pivot column, pivot position is at the top. This should be the pivot position. Though it is at 0 here, we can exchange the rows. So this should be the topmost position, should be the pivot position. So this is the pivot column, since it is non-zero column. So let us exchange the columns. We can exchange any one of the rows, second row or third row, into the first row. So step 2, select a non-zero entry in the pivot column as pivot. If necessary, interchange rows to move this entry into pivot position. So here we observe that there are 2 non-zero entries. So I can interchange R2 to R1 or R3 to R1. I have 2 options. Of them I have selected the third row. I have interchanged row 1 and row 3. R1 interchanges with R3. You can also make the interchange with R2 also, of course. So third row, now the third row will become first row to row. First row goes to third row. Now this is the new matrix after the interchange of rows. So this is the pivot, and these two are the other two rows. This is the pivot column. Now the third step. Use row replacement operations to create zeros in all positions below the pivot. We need to make these two are zeros. This is already 0. That's why I need to make it 0. Using row replacement operations. So as a preliminary step, I can divide this with 3, since all the entries are multiples of 3, but for convenience, to make this 0, simply I can subtract one from another. R2 goes to R2 minus R1. That is enough. Or you can multiply this one minus 1 and add to this one. So after doing this, this will also become 0. So first I identified the pivot column and make sure that the pivot position is non-zero by interchanging the rows. Later we made the below entries as 0. We made the entries below this pivot position or leading entry zeros by using elementary row operations. Step 4. Cover the row containing the pivot position and cover all rows if any above it. Apply steps 1 to 3 to the submatrix that remains. So I am covering this first row which has a pivot position. So now the gain is in this submatrix only. So in this submatrix, I have to find out the pivot. So that must be the first non-zero entry, that is here. So it is non-zero. If it is 0, I can exchange these two rows. If this is also 0, I will move on to here. This will be my pivot position. Luckily, this is a non-zero, so it is my pivot position. Since it is a pivot position, it is the second pivot column. Next pivot column. This is the next pivot column. Now using this, I will make this as 0. So I can multiply with third row with this number 2. Now I can subtract this row by multiplying with. Or we can simply directly make a unit using this, make 1. So we add minus 3 by 2 times the top row to the row below. This produces this matrix. So I am not touching the first row. Second row is also same. In the third row, we are doing elementary operations to make this 0. And similarly, these remaining entries will also change like this. So this is my new matrix, which is equivalent to the original matrix. So when we cover the row containing the second pivot position, so step 4, we are left with the new submatrix having only one row. So after completing the exercise, we can cover the rows containing the pivot positions. So these two rows are covered and only one row is left. So this is the pivot position. So this is the matrix which is in echelon form. So now the matrix is in echelon, required matrix of echelon. So here you can observe that this is the leading entry and the entries below this one are zeros, and this is my second leading entry, pivot position, and the entry below this entry is again 0, and in the third row this is the leading entry, this is the pivot position. So now this matrix is in echelon form. Let us convert this into reduced echelon form. So to convert this into reduced echelon form, two more steps are to be performed. So beginning with the rightmost pivot and working upward to the left, create zeros above each pivot. If pivot is not 1, make it 1 by scaling operation. These two are to be done. One scaling and another making zeros above the end. So here it is already 1. Using this 1, we make these two zeros by using these two operations, row operations. By using these two row operations, we can convert these two into zeros. Similarly, we can make it 1 by dividing the second row with 1 by 2. So this was right 1. Using this 1, we can convert this into 0. by using the elementary row operation, this one R1 is added to the 9 times R2. Minus 9 plus 9 will become 0. Similarly, remaining elements will change like this. So now it is in reduced Echelon form, except this 3. This 3 can also be converted into 1 by dividing with 3, or by using scaling property. It is scaled by 1 by 3. R1 goes to R1 by 3. So now all the leading entries are 1, and except those leading entries are pivot positions, no other entry is there without a 0. So these two are zeros. All the other entries are zeros here. All the other entries are zeros. All the other entries are here also. So 1, 3, 5 are the pivot columns. These 3 are the pivot positions. Now it is in the reduced Echelon. So this is the way to convert a matrix into reduced Echelon form, which will be very useful in finding solutions of equations and to check the given vectors whether they are linearly dependent, independent, and to find basis at later stages. So this is the prerequisite for this topic. And being a subset of the original subspace, original vector space, we call it as subspace of original vector space. And this is one more definition which we have come across: linear combination. Any sum of scalar multiples of vectors is called linear combination of vectors. Using mathematical notations, we can write this as, let V1, V2, and so on, Vp belongs to V, the set of vectors, and C1, C2, Cp are the scalars. Then any vector y defined by y is equal to C1, V1 plus C2, V2 plus so on plus Cp, Vp is called the linear combination of the vectors V1, V2, and so on, Vp with the weights C1, C2, so on, Cp. So any vector which can be formed using these vectors by this notation is called the linear combination of two vectors. And finally, span of v1, v2, and so on, vp is the set of all vectors that can be written as a linear combination of v1, v2, and so on. So the set of all linear combinations is called span. Span is the collection of all vectors that can be written in this form: c1, v1 plus c2, v2, and so on, cp, vp, where c1, c2, cp are the scalars, and this is the set rotation of this span v1, v2, and so on is equal to set of c1, v1 plus c2, v2 plus so on, cp, vp, such that c1, c2, and so on, cp are scalars. So these are all the things which we have gone through. So I am quickly wrapping them. And now today's definition: linearly independent set. An indexed set of vectors v1, v2, and so on, vp in V is said to be linearly independent if the vector equation c1, v1 plus c2, v2 plus so on plus cp, vp is equal to O. O is the zero vector in the vector space, has only the trivial solution. If this relation has only the trivial solution, what is the trivial solution? C1, if C1 is 0, C2 is 0, and so on, Cp is 0, then the left hand side is equal to the zero vector O, and the right hand side is also O. So all the scalars are zeros. That is the trivial solution. C1 is equal to 0, C2 is equal to 0, and so on, Cp. So if this relation has the trivial solution only, this is obvious. You will get this solution anywhere. So Whenever C1 V1 plus C2 V2 plus so on plus CP VP is equal to O, C1 C2 and so on CP must be equal to 0, then we can say that the set of vectors, indexed vector, indexed set, this is indexed set, that means we are doing numbering to them so that the order is preserved. So that set is called linearly independent set. So for a linearly independent set, there will be no solution other than the zero solution. Whenever you are taking an equation like this, C1 V1 plus C2 V2 plus so on, CP VP is equal to. For example, let us take a 5 rupee coin and 2 rupee coin. So here my V1 is 5 rupee coin and V2 is 2 rupee coin. So 0 is 0. Let us take the 0. In our vector space, 0 is 0. So now I have to find C1 and C2, non-zero C1, C2, so that relation C1 5 plus C2 2 is equal to 0. So we can find that in real numbers or any scales. 2 into 5 plus minus 5 into 2 is equal to 0. So I can find non-zero C1, C2. So those are linearly dependent. 5 rupee coin and 2 rupee coin is linearly dependent when I am using real numbers as scalars. But here in this case, you can't find such scalars. So for example, V1 is a pen, V2 is a pencil. C1, C2 are scalars. For whatever C1, C2, you can't get a O. Of course, you have to define O also in your set of objects. That should be a vector space. So you can't find that. If you can't find that, that is a linearly independent set. If you find C1, C2 such that this relation holds other than this zero solution, then that is linearly independent. Linearly dependent set. The set of V1, V2 and so on Vp is said to be linearly dependent if C1 V1 plus C2 V2 and so on CP Vp is equal to 0 has non-trivial solution. The example which we have seen earlier, 5 rupee coin and 2 rupee coin, I find a non-trivial solution. C1 is 5 is 2, C2 is minus 5. So that is a linearly dependent set. That is, if there are some weights, here we call these scalars as weights, C1, C2 and so on CP, not all 0, such that C1 V1 plus C2 V2 plus so on CP VP. To show that it is a linearly dependent set, we need to find at least one non-zero scalar in this relation. At least one of C1, C2 and so on CP must be a non-zero. Then we can say that it is linearly dependent. Otherwise, the set is linearly independent. Linear dependence relation. In such a case, where you find the set is linearly dependent, the relation C1 V1 plus C2 V2 plus so on plus CP VP is equal to O. So the zero element, zero vector in vector space P is called a linear dependence relation among V1, V2 and so on. Set of, let us look into some of the sets which are linearly dependent and which are linearly independent. Set of one vector. A set containing only one vector, say V, is linearly independent if and only if V is not the zero vector. If V is zero vector, then that is linearly dependent. If it is a non-zero, 5, only 5. 5 is a linearly independent vector. Or I can take a matrix 5, 1. Then since there is only one vector, it is linearly independent. Since xv is equal to O, has only the trivial solution, x is equal to 0. So if I find only one vector v, so c1 v1 plus c2 v2 and so on plus cp vp is equal to 0. In that relation, there is only one vector. So my equation reduces to x c1 v1 is equal to 0. Here my v1 is v. So instead of c1, I take x. So xv is equal to O. Since if v is not a non-zero vector, then x must be 0 from one of our properties of vector space. So since x must be 0, so whenever xv is equal to 0, x must be 0. So the equation has only trivial solution. Then we can say that the set of v is linearly independent. So if we have two vectors, u and v, so let us consider the case of two vectors. A set of two vectors u1 v1 is linearly dependent if at least one of the vectors is a multiple of other. So if one vector is a multiple of other, you can say that those two are linearly dependent. In the earlier case, 5 rupee coin and 2 rupee coin, one is multiple of other when the real numbers are scalars. If I multiply with 2 by 5, a 5 rupee coin, I will get 2 rupee coin. So that is 2 by 5 is my scalar. So if one is multiple of other, then we can say that those are linearly dependent. The set is linearly independent if and only if neither of the vectors is a multiple of other. If we can't write vectors as a multiple of other, we can say that those vectors are linearly independent. For example, 3, 1 and 6, 2. If I multiply this with 2, I will get this one. So on scalar multiplication, I will get this one. So these two are linearly dependent. This is another example. I can't get this by multiplying with 2 or any scalar. No scalar will give you the 6, 2 from this 3, 2. So these two are linearly independent. So these two are not multiples of each other, one another. And this is a multiple of this one, this is a multiple of this one, of course. If I multiply with 1 by 2, I will get this. So these are linearly dependent, and these two are linearly independent. So this is the case of two vectors. Let us discuss about a set containing more vectors, more than two vectors. So in the set containing more vectors, then there are the entries in each vector, then the set is linearly dependent. So if the entries in each vector are more than the vectors, it is opposite to that. There must be more vectors than the entries in each vector. Then we can say that it is linearly dependent. That is, any set V1, V2 and so on Vp in Rn is linearly dependent if P is greater than N. You know that in Rn there will be n entries. If I take more than n vectors, then the set containing those vectors is linearly dependent. For example, these three I have taken three vectors of two entries. These three are vectors of R2. So it has three vectors. So there will these three must be linearly dependent. Any number of vectors that is more than entries, that is linearly dependent. If I take R20, if 25 vectors are given to me, then simply I can say that those 25 vectors are linearly dependent. Without verifying anything, I can say that. Since there are more vectors than the entries in those vectors. So set containing zero vector. If a set yes is equal to set of V1, V2 and so on, Vp in Rn contains zero vector, then the set is linearly dependent. So any set in which there is a zero vector, that is linearly dependent. Since we can write in this manner, V1 is 0, then I can write 1 into V1 plus 0 into V2 and so on, remaining all zeros, that is 4. Since all are zero vectors, since remaining are all zeros, 0 into some vector is zero vector. These are all zero vectors. And since V1 is zero vector, 1 into 0 is again 0. So left hand side is zero vector. So addition of zero vectors is again zero vector. So here I can find a non-zero scalar 1. Here 1 is a non-zero scalar. I could find a non-zero scalar so that the relation is satisfied. So this is a linearly dependent set. Whenever there is a zero vector in it. So these are the rules for finding the vectors, whether they are linearly dependent and independent easily.